Okay, so I've drawn a picture of what we have over here on the left-hand side. We have a fish that's the shape of a ball. That's the red piece in here. And it is kind of jammed, packed tightly inside of a cube that is blue in this case. And they ask me some questions. They say stuff about the volume changing for the fish. So maybe I'll write that right here. So this is dV dt for the fish. All right, F. And then they want to know what is the surface area. So d SA dt for the cube. Equals what? And then they also give me this piece right here, which we'll talk a little bit later about how we're going to use it. If you remember, there's kind of 4 steps. This 288 is going to come in to play in the last step, I believe. Actually, let me just use it now. I'm going to take care of it now. I know that the volume of a sphere, of a ball, is 4/3 pi r cubed. If I go and plug in, so this says volume of puffer fish. If I go and plug in 4/3 pi r cubed to that, or and set it equal to that, so I'm going to multiply that by 3, divide it by 4, divide it by pi, cube root it, then I get r equal to 6. So that's why they give me that. Maybe I'll circle that in green because it's important and we're going to use it later. So this is dV dt for the fish, and dSA dt of the cube is what we're looking for. Alright. So I'm going to actually go straight from that red formula that I have right there. That's the volume of the fish, and they give me dV dt for the fish up there in green. So I need to get dV dt, so I'm going to take this guy and I'm going to derive it with respect to t. That gives me, and so I'll keep v sub f so that I know what I'm talking about. So dVf dt is equal to, so I derived that left-hand side with respect to t. There's no functions, it's just the v, so it's just dV dt. For the right side, we've got our cube, and I need to do power roll on it. When I do power roll on it, I get the 3's cancel because I do 3 times 4/3. So that gives me 4 pi r, and then when I do the power roll on the r cubed, it drops down to r squared, and then I need to do the derivative of the inside piece, and what I mean with the inside piece is the inside piece of the cubed piece, which is r. So the derivative of that, since I'm deriving with respect to t, is dr dt. Okay, so the general process for this one is going to be, after I do that, I mean, you should kind of figure that we have to do that based on this right here. So what I'm going to do is I'm going to figure out what dr dt is. And then I'm going to go ahead and maybe I can write it in blue up here. So if I go to the center of this guy right here, of the cube in the top face, and I go out like that, that is going to correspond with the radius. Same thing this way, right? So this is r, that's r. So if I were to go and like shade that top section right there, that would be r squared. So eventually I'm going to use that. I want to know what's the surface area of the cube changing. So I'm going to use that to figure out how the surface area is changing. The surface area is related to the r. So if I know how r is changing, then I get dr dt and stuff like that. So anyway, I'm going to plug in this right here, that 12. It's dV dt. So I get 12 centimeter. I'm not going to write my units. 12 equals 4 pi. I know that r is 6 right there, so I'm going to use that. So 4 pi times 6 squared times dr dt. So let's divide by 4, right? That gives me 1/3 on the left side. Or sorry, yeah, no, that gives me 3 on the left side. And then when I divide the 3, so boom, boom, 3. Now I divide by 36. 33 goes into 36 12 times. So if I divide by everything there on the right hand side, I get 1 over 12 pi equals what's left, which would be that, dr dt. Okay. So from here, I'm going to scroll down a little bit. Remember that I'm looking for how is the surface area changing. So I will make a little line, do the rest of my work down here on the right hand side. Actually, before I do that, remember that little block up there was r squared. If you think about it, there's 4 of those on each face, right? I could go put another one in the back left corner, front left, and then front right, right? So there's 4 of those. So each face, there's 4 of them. So I get 4r squared. I'm looking for the surface area of the whole cube. From there, I know that there's 6 faces. So I do 6 times 4r squared to get my surface area. So SA of the cube is equal to 24r squared. So I'm going to actually write that over here on the right hand side. And I'm just going to write SA, because that's the only surface area we really care about in this case, equals 24r squared. So now I need to do the same process I did over here with the volume. I know dr dt, right? I've got r, I've got surface area. I'm looking for, just up here, remember that? I'm looking for the dSA dt, how is the surface area changing with respect to time. So I will green this, because we're going to use that. So I need to derive with respect to t. dSA dt equals 2 times 24 is 48. R, the power rule drops it by 1. And then I need to multiply it by the derivative of the inside piece, so dr dt. Notice it's got an r, which I have one right here, and it's got a dr dt, which I have one right there. So I can figure out how the surface area is changing by simply plugging in those 2 purple arrowed values. So I get dSA dt is equal to 48 times 6 times 1 over 12 pi. Now I just have to simplify. So I will scroll down a little bit now. I'm going to divide 12 into 6, and it's going to leave me with a 2. Then I'm going to divide the 12 into the 48. It gives me 24. So it simplifies to 24 over pi. If you were going to give your units, you should recognize, we could go through and put units on everything in this, but it would be a lot of work and it would totally jumble everything up. We're talking about surface area, how it's changing in respect to time. So my units are centimeters squared, because we're working in centimeters, per second. Hope that helps.